The Arrhenius equation is used to link the fraction of molecules with energy greater than the activation energy with the rate constant. Okay, it looks pretty disgusting. I'm going to take each of these components in turn and explain them to you. So remember K we've met before, that's the rate constant, whose units we'll have to determine separately. EA up here is your activation energy. T is your temperature in Kelvin. R you met at the ideal gas equation, it's your gas constant, which has a value of 8.31. Now this E here is an exponential, which is just a maths term, which means the A here, because it occurs before your exponential, it's your pre-exponential factor. Which has the same units as your rate constant. Don't worry if maths isn't your strong point and you're feeling a bit freaked out by all of this. I'm just going to give you a simple list of steps you can follow, which will help make sure you know what you're doing in the exam. Now, we're trying to plot a graph fundamentally here. In order to do that, we need to get this Arrhenius equation into the format of a straight line, which is y equals mx plus c. Bear that in mind. So the way in which we go about that is by taking natural logs. And the reason you take natural logs is it allows you to remove that exponential. So if I take a natural log here, it will remove my exponential, but I need to make sure I take a natural log of everything in your equation. So this is why I'm allowed to write this, because I've taken a natural log of it. And I must remember to take a natural log of my pre-exponential factor also. So that's what's happened here. I've taken a natural log here, and by taking a natural log here, I've removed my exponential. If you're not comfortable with exponentials and natural logs, don't worry. Just make sure you can find these buttons on your calculator, and do make sure you learn these equations off by heart. Now let's get this into the format of y equals mx plus c. Just put that here. That's your equation of a straight line. So we've got your natural log of k, the rate constant. We're just going to separate our fraction here in order to give us an equivalent of m, the gradient, and x. So just take a step back, look. What I've written here is exactly the same as this. I've just separated out the r and the t in effect, keeping our natural log of that pre-exponential factor. So just to really show you what we've done here, we've taken that Arrhenius equation, and by taking natural logs, we now have it in the format which lines up with our y equals mx plus c. So now we're ready to draw a graph. So our natural log of the rate constant goes on the y-axis. We can see here that our x is 1 over t, so that forms our x-axis. I'm just going to add the units here, which is obviously temperatures in Kelvin. It's 1 over temperature, so that's why it's k to the minus 1. The y-intercept, which remember is given by c, is the natural log of our pre-exponential factor. Okay, for argument's sake, I've just got a line plotted on here. I'm now going to show you what we can work out from said line. So remember, c is our y-intercept. We know it must be the natural log of a, so that's here. The gradient now, m, is this term here. It's our activation energy divided by the gas constant. So it's therefore a pretty straightforward step in order to calculate the activation energy, because we know that R is always 8.31. So when there are actual numbers on these scales, you can work out your gradient, sub in your 8.31 as your R value, and that will enable you to calculate your activation energy. Just make sure you're mindful of units. I will show you an example now. So let's put into practice what we've just learnt. So use the Arrhenius equation in the graph below of natural log of K against 1 over temperature for the reaction shown to calculate the activation energy in kJ per mole for the reaction. So remember, the activation energy we pull out by looking at the gradient. So gradient M is given by change in Y over change in X. So my change in Y is going to be here. My change in X will be along here. Just read carefully down these scales and you can see our change in Y is minus 14.1 minus 2.8 divided by our change in X, which is 0.0018 minus 0.00128 to give us a gradient of minus 21,731. Let's take the Arrhenius equation in the format of y equals mx plus c, which remember is the natural log of the rate constant. So remember I said you needed to learn this equation. There's our y, our m, our x and our c. Remember that we said that the gradient is our activation energy divided by our gas constant R. We've just calculated the gradient. We know that R, the gas constant, equals 8.31, so just cross multiply and then get rid of your minus signs to get an answer which is 180,583 joules per mole. Final step is to get that into kJ by dividing by 1,000. So just to remind you, what did we do? We wrote out our Arrhenius equation in the form of y equals mx plus c. We pulled out the fact that the gradient is equal to minus the activation energy divided by the gas constant. We found the gradient using the graph. We substituted in our values, remembering that the gas constant equals 8.31. And then we finally did a unit conversion to get a final answer of 181. Right, the second part of the question, a reaction has a rate constant of this value at this temperature. Use the equation to calculate a value for the activation energy. That pre-exponential factor A equals this and the gas constant is this. So I've written out this equation. I've just popped RT down there so I can see it more clearly. Let's rearrange to make activation energy the subject of the formula, so we need to multiply everything by RT. I'm going to add the activation energy to both sides. And then just take away that natural log of the rate constant multiplied by R multiplied by the temperature. And then look, let's take RT out as a common factor. Let's substitute in our values. R, remember, the gas constant is 8.31. The temperature we've told is 356 Kelvin. We'll do a natural log of A minus natural log of the rate constant. So our final answer here is 86,094 joules per mole. Let's get that into kJ by dividing by 1,000. To recap, we take the equation in the form that they've given us. Then we rearrange the formula to make the activation energy the subject of the formula. We take out the common factor of RT and then we substitute the values in from the question, remembering to convert to kilojoules at the very end. A slow reaction has a rate constant at 300 Kelvin. Use the Arrhenius equation to calculate a value in kJ per mole for the activation energy of this reaction. So we're looking for EA. We've been told that A equals this and R equals this. So let's write down the equation. We need to make the activation energy the subject of the equation. So multiply everything by RT. Add EA to both sides. Take out a factor of RT. And then substitute in your values. R equals 8.31. The temperature we were told is 300 Kelvin. A is 2.57 times 10 to the 10. The rate constant was 6.51 times 10 to the minus 3. Put that into your calculator. That's in joules per mole. So just divide by 1,000 to get it in the appropriate unit. A second series of experiments was carried out to investigate how the rate of the reaction varies with temperature. The results were used to obtain a value for the activation energy. Identical amounts of reagents were mixed at different temperatures. The time taken for a fixed amount of bromine to be formed was measured at different temperatures. Complete table 3. So here we're being asked to find the natural log of 1 divided by t. So press the natural log button on your calculator and then do 1 divided by 27 to get minus 3.30 to 3 significant figures, and then to fill in this row all you have to do is 1 divided by temperature, so 1 divided by 302, which is 3.31 times 10 to the minus 3. The Arrhenius equation can be written as, in this experiment, the rate constant K is directly proportional to 1 over T. Therefore, you can write it as this, where C1 and C2 are constants. Use values from table 3 to plot a graph of natural log 1 over T on the y-axis against 1 over T on the grid. Use your graph to calculate a value for the activation energy, and the value of the gas constant is 8.31. So they've already told us what's going on the y-axis. It's the natural log of 1 over T, so that's what we have here. It means that we are looking at this particular column here for our scale. So as you can see, it goes sensibly down from -2 to -4, and then 1 over T we've already been given in this particular question along with the scale. Then we're going to plot a graph. I've done that too. We're plotting on the y-axis -3.99 against 3.5 times 10 to the minus 3. So that's that point right here, and so on and so forth. And now the hardest bit is to find the activation energy. First thing, remember that this equation here is in the format y equals mx plus c. So we can see therefore that the gradient is minus activation energy over r. So let's write that down here. So let's work out the gradient of this line, which remember is change in y over change in x. So I'm going to create a triangle right here for you to just see what I'm doing. So that's my change in y, that's my change in x. So my change in y is minus 4.0 minus 2.0. Read off your x values carefully using your x scale. So you can see that's 3.50 times 10 to the minus 3 minus 3.20 times 10 to the minus 3 equals minus 2 over 3.0 times 10 to the minus 4, which equals minus 6.667 as your gradient. So substitute that in. We know that the gas constant is 8.31. Multiply both sides by 8.31 and then take out the minus sign to get an activation energy, 55,400 joules per mole, and then finally divide by 1,000 to get it in kJ per mole to get 55.4.